All right, well, thank you everyone for joining us this morning for today's event on the Future Vertical Lift, our series on Future Vertical Lift, focusing today on the Joint Multi-Role Technology Demonstration. We've got a great panel here to inform you about this effort. But before we dive into the substance, give our obligatory security announcement. We've got a very secure facility here, but we have thought through what to do in case anything were to arise that would make us need to leave the facility. And if that happens, I will be your security officer, and I will give you further instructions, and the voice of God will descend upon us and tell us when we have to do that. But that's extremely unlikely. So, but I did want to make you aware that we have thought that through and that I'll be guiding you if that happens. I also want to thank our sponsors as we get started. This whole Future Vertical Lift series has been made possible by support from Textron and Bell Helicopter, so we want to thank them for making this possible. As I mentioned, we've had a series on Future Vertical Lift. It's been on a brief hiatus while we were getting ourselves organized to go for the next round of sessions, but we're getting back into it. And we've had a number of excellent discussions previously focused on the opportunities for commonality in Future Vertical Lift, how that's being thought through, how that's being worked, how industry is looking to implement that, the sort of unique nature of the government-industry partnership that the Future Vertical Lift program has demonstrated, which is fairly unique, at least in recent years, and how the Department of Defense has pursued a new innovative capability. And a little bit we've heard about the timelines and the various capability sets that the program has been looking at. Today we want to focus on the technology demonstration. We've had a previous event on this a couple of years ago. There's been a lot of progress made by the teams. And in particular, we're going to focus not just on the air vehicles, which are, if you haven't seen them, really cool looking and are worth checking out. And if you're going to be around for AUSA in a week or so, I think you'll get an opportunity to see them, if I'm not mistaken. But also the mission systems aspect, which is, I would argue, equally important part of the effort. And to find out more about all of those things, we're gonna work from left to right on this panel. And our first panelist who's going to talk to us is Dan Bailey, who is Program Director of the Joint Multi-Role Future Vertical Lift effort at the Army Aviation Missile Research Development Engineering Center. And he was here the last time we talked about the JMR-TD, since he's the qualified expert from government to talk about it. He's a West Point graduate and career aviator, test pilot, and an acquisition professional, so he's a multi-threat performer. And Dan, without further ado, why don't you kick us off?
Okay, thank you, Andrew. Hey, good morning. Appreciate you coming out. So, as Andrew said, I'm the government representative here, so I don't have a lot of new things to say, but I'll try to say a few. And but what I want to say is our partners up here are really going to tell you all the new aspects of it. I'm going to set the framework for a little bit of that. Just refresh and tell those who haven't been involved what we're doing, what we're all about, if you will. So the first thing I'll tell you, if you'll bring up the chart, there it is. The Joint Multi-Role Technology Demonstration is not Future Vertical Lift, right? Two separate efforts. One is an intention for a family of systems, Future Vertical Lift, and it's an initiative to bring forward a next-generation vertical lift capability for our defense. We have a growing program of record, if you will, moving towards an acquisition decision, but I'm going to tell you up front today, the intent's today not to talk about that, right? There's going to be future events intended to talk specifically about that as before the calendar year is up, I would say that. So today we're focused on the Joint Multi-Role Technology Demonstration piece, JMR-TD. What is it? It's a system-level demonstration within the S&T environment to set the conditions for a successful Future Vertical Lift program, okay? And follow on to that, a family of systems as we replace all of our vertical lift capabilities in the Department of Defense over the coming, really, centuries, right? So, and I say centuries with a joke, but it's a long time. It's going to be a while. It's not going to happen overnight. It's not going to happen all at the same time. So just as it's taken us years to get what we have today in vertical lift, it'll take us years to get a next generation capable vertical lift. So what you see up there is a timeline, small calendar there. What I'll tell you is JMR-TD kicked off formally in 2011, has progressed on. It is going to end in 2020. Formally, the air vehicle piece will end in 2019. Mission system architecture demonstrations will go through 20. We'll talk about that more in effort as we go forward. What are we doing, right? We're demonstrating both the platform and mission system architecture. Those are two separate focused events, obviously linked together in the understanding, but they are two different separate events. And you can see that the air vehicle demonstration piece, that's what our partners are going to talk about, are moving along very nicely. We're in the second of our mission system architecture demonstrations, and I'll talk about that a little bit more in just a few minutes. You know, the pictures give you some idea that we're doing 2 aircraft flight demonstrators, a couple of other technology demonstrations, advanced technology demonstrations, and we're doing a series of architecture demonstrations. Look at the outcomes. The outcomes there are what's really key, right? So those platform level demonstrations give us the confidence that we can actually build a next generation vertical lift capability to satisfy the warfighter needs. That's a big deal. We have the ability, partnering with industry this early on, as Andrew said, it's very unique to have government parametrics to know that we can actually do this successfully, we can do it affordably, we can do it efficiently. Those are big deals for us, right? We don't want to take off on this path and not be successful. So we're setting all the success up front. And the standards and references, all of those are fairly, old, right? Our designs are from the 60s and 70s on our current vertical lift aircraft for the most part. So the standards that we use for those all have to be refreshed. We're using the S&T environment to refresh those over time. So go to the next chart. So what is it we're after on the air vehicle piece? The future operating environment demands a vertical lift capability that's greater than what we have today. And the designs we have today are fairly limited from a physics perspective of getting much more out of that platform. Not to mention that they have been upgraded successfully by industry for decades, but the ability to upgrade them efficiently continues to go down, right? So economically, we need to move to a new platform. And these give you an idea of, after we did a capability-based assessment with the requirements community, we in the S&T community developed what's called a model performance specification. The model performance specification would be like any other specification for an acquisition development program. We took that, we gave that to industry, we gave it to our government design teams, and partnered together. They have moved forward and come up with conceptual designs. We've chosen some conceptual designs out of that work to move forward to flight vehicle demonstrations. And you can see some of the capabilities there that we're after. Next chart. So what about the architecture piece? I'm very glad to hear Andrew say that the architecture is as important. It's not only as important, it's more important in a lot of ways. The air vehicles we have out there today have been out there for a long time. They will be out there for a long time. We change rotor blades, we change transmissions, we enhance performance, but in general, the operating environment that we will see in the future is much more subsystem technology oriented, right? We're going to need capabilities for the warfighter on a very rapid acquisition perspective. And the way that we can get after that is open system architecture. That's not new, right? So we've heard for a couple of decades now, we're after open system architecture. What's different about this? I will tell you, as the ex-Apache Block 3 PM, now the 64E, open architecture was a big part of the program. So I inherited that. I finished the development on that as the government PM, fielded that aircraft, and we made success. But in general, the Department of Defense has been after open architectures within program of records, formal acquisition programs in the past. So you enter with what you think you know, and you move forward with that through the development, right? It's very difficult for a PM, I know, to change the course of that during that process. You're worried about the cost, schedule, and performance. You can enhance it a little, but generally what you set off with, what you know as the standards, processes, the tools, are what you have to proceed with. Well, that constrains you somewhat. So what's different about this? We're doing the same kind of thing as you would in the development of an architecture in incremental fashion, right? Through demonstrations, increasingly complex demonstrations that are indicated on that bottom chart in the schedule. Through those complex demonstrations, we are experimenting and demonstrating various facets of what gets to open system characteristics, right? The standards, the tools, the processes. So we want to give the Future Vertical Lift initial program, and therefore the family of systems after that, a set of standards, processes, tools, and implementation guide, if you will, to say this is the line that you need to draw. We don't know what that line is today, but it's new in that we're doing that through resourcing S&T to do that. So S&T in the past would go after a mission processor, right? The box. Maybe go after fiber optic channels. But bringing it together in an architecture demonstration, I would say that's very new. Okay? I like this chart simply because, to me, building an architecture is putting a whole bunch of pieces of a puzzle together. It's as much about the acquisition strategies as it is about the standards and tools and processes. That acquisition strategy is pulling together various elements of a puzzle, putting them together for what your solution has to provide to you. Every vehicle will be a little different, right? An attack aircraft versus a utility assault aircraft might be a little different. So the architecture might be slightly different, but how far can you drive the open characteristics into that architecture? That's what we're trying to demonstrate under MSAT. So with that, I'll turn it over to the industry partners who really will give you the background on where we are today.
Great, thank you, Dan. First up, we have Pat Donnelly from Boeing, Director of Future Vertical Lift at Boeing. He's held various positions at the company prior to this one, including Program Director, Advanced Rotorcraft Systems, and Program Director for the MH-47G Chinook, and been Director of U.S. and foreign military Chinook programs. Pat, please give us your view on what's been going on.
Thank you. Well, certainly, first off, I am very pleased to represent the Sikorsky-Boeing team as we execute JMR. If you go to the next chart, what is our product? So we're building the SB-1 Defiant. It is a third iteration of a lift coax aircraft. And as such, just some of the highlights of our vehicle, really driven by that pusher prop in the back. The pusher prop allows us to accelerate, decelerate up to 250 knots. And we have the coax blades that give us a very responsive aircraft. As you look at it now, all composite fuselage, we sized it kind of close to what Dan talked about from the MPS spec, with a cabin for 12 combat-equipped troops of the right size that was specified in the MPS, and we're moving along. So if you go to the next chart, we have certainly taken a very disciplined approach, recognizing it's still a tech demonstrator, but still doing very disciplined as we move forward in this aircraft. Certainly the vehicle itself was designed, 3D modeled and designed, as you would in any vehicle that we're doing these days. A lot of extensive wind tunnel testing. As a matter of fact, we are wrapping up yet another wind tunnel test out at the NFAC in San Francisco, where we have a powered model with powered props to validate all of that activity. We have been developing fiber placement, 3D printing, modeling, and certainly an extensive use of pilot simulation, not only in the Stratford facility, but also in the Philadelphia facility. If you go to the next chart, so the key elements of our activity is around risk reduction. So we have a fully populated systems integration lab, electrical, hydraulic, complete cockpit representative of the vehicle itself. And that is validating, as we speak, all the software, electrical, and hydraulic elements of our design. In the lower left corner is our propulsion system test bed. We're building that as we speak down in West Palm Beach, Florida. And that is going to be used to develop and to validate all of our mechanical systems. So we'll have engines, transmission, and all of the moving parts will be in that system. And then finally, it'll all culminate in our flight vehicle. The flight vehicle itself, if you go to the next chart, so where are we? We are readying our fuselage for structural verification testing that we'll conduct by the end of the year. We are building rotor blades. We are assembling our main transmission. We are machining all of our drive shafts. And, as we build this up, we are actually building essentially two sets of everything. It either goes into our systems integration lab or it goes into our propulsion system test bed. And it's all going to culminate as we fly the end of next year.
Great, thank you. Next, we have Vince Tobin. Vince is Vice President, Advanced Tilt Rotor Systems, Bell Helicopter. And Vince, thank you for joining us.
Sure, thank you. Thanks to CSIS for the opportunity. I also want to say thank you to the Vertical Lift Consortium for their role in helping get this organized. So I appreciate that as well. This is my only chart, and That photo that you see there on the right half, that is the actual air vehicle. It's 65% built. Actually, it's probably 64.6%. We just rounded that up, but the point is we know exactly where we are. We count the number of workbooks in total that we're going to build, and we that's the denominator, and then we figure out how many of them we've completed based on some difficulty calculations, and we get a number. And we're very interested in that because that tells us how we're doing on the build, how we're doing from a cost perspective. We're very interested in that. The fact of the matter is we looked at a V-22 pretty far down the learning curve to establish the baseline for where we are, and at that we're exceeding a 1.3 CPI. I know that may be geek acquisition speak. For those not familiar, that means we're getting about $1.30 plus of value for every dollar that we're spending against what we thought was a pretty tough standard. So we feel good about what we're demonstrating from a cost perspective going forward. Obviously, the whole reason for this JMR-TD is allow us to make the case that all the technologies that we need for this program, again, I'll qualify that for the requirements as we know it now, but all the technologies we need are TRL-6 or better, and when we fly this in September of next year, we'll demonstrate that. Where we are going forward, again, 65% built. What you'll note there is that those nacelles, as beautiful as they are, non-rotating, are not filled with engines or gearboxes yet. We're building gearboxes. We have engines on hand now, ready to go in there. We'll get engines and gearboxes into the aircraft this November, and we'll start turning rotors shortly thereafter, going through a pretty extensive verification process. Ground runs, et cetera, that will get us to first flight September, and not later than September of 2017. The other thing I wanted to talk about a little bit is the digital thread, how we design this. The benefit that we're getting from it is that using true 3D modeling, parts fit together. But the other thing is we did our drawing structure in a way that we've been able to flow that to planning, so that one planning function that we did on V-22 that we mapped with 2D drawings that took 900 hours. With the aid of multiple software programs, we got that to about 40 hours. So not only are we getting a good design with parts that fit together, but we're accelerating the planning process. What we also expect to do with that is to be able to flow that down into maintenance manuals so that we can improve the maintainability of the aircraft as well. What that will require is a change in the approach of how we contract things. As opposed to 2D CDRLs where we submit lots of paper documents, more licensing of software and the ability to look at the same data we're looking at real time. From an open system architecture perspective, what we're really looking for is simply modular partitionable systems where what we put in there is hardware with space, weight, and power, so that the software is truly modular, where we can change things quickly. It's good for us. It's good for our customer. The reason why it's good for us is if we can get capability into the aircraft more efficiently, less expensively, it allows us to market the aircraft more readily. So we're all in. What we really want is the capability for some kid in the basement. May not be that easy, but somebody that looks and says, hey, look, if I get this data and this data, I piece that together, I have a capability, and it may be a capability that none of us ever thought about. We want that opportunity to be out there for folks to make the aircraft better. The other thing is we don't want to be afraid of open system architecture. Our view is we want to give the government, if they wanted to have the capability to be the integrator, while they have the capability to be the integrator, we would recommend that maybe we would ask them to allow us to continue to do that. But what giving them the capability does is it keeps us honest. It makes sure that we're doing the right things to keep costs down. Lastly, I'll say we talked yesterday about V-247. That's our next effort. Bell Helicopter's continuing to invest in tilt rotor technology. We believe tilt rotor is the future of vertical lift, and we're going to continue investing in it.
Thanks, Vince. Next, we have, I believe, Ryan. Ryan Bunke, who is a manager, special operations for Air Force and Advanced Rotor Ring Programs at Rockwell Collins. He's the program director who's leading the mission systems demonstration effort within Rockwell Collins.
Good morning. Thank you. Thanks to CSIS, Mr. Bailey, and the Vertical Lift Consortium for the opportunity to come and represent ourselves and our industry partners who are working in the MSAD side of the JMR effort. From our perspective, we really see the MSAD effort as the leading edge of what open systems are today. So Dan touched on in his intro, open systems aren't new. We've been talking about it as an industry for a number of years now, but what we see is really over the last 5 years or so, industry has started to coalesce around some more firm definition of what open systems mean, and you're starting to see that in the codification of technical standards like FACE, the Future Airborne Capabilities Environment, and HOST and JCA. And as Dan mentioned, what makes the MSAD piece a little bit different is, in addition to proving out those concepts and providing some risk reduction towards how we use those in the future, we're introducing the tools and the processes that support that, things like model-based engineering and virtual integration, and really both from, I guess the piece I would add to what Dan said, proving it out both from the technical perspective, but also from the business model perspective and how we work that within today and potentially tomorrow's acquisition environment in terms of using models as specifications and interchangeable pieces between multiple vendors. But a little bit of why this open systems piece is important, and Dan touched on it a little bit. But from our perspective, what we're doing through MSAD is really reducing risk and informing what that mission system environment will look like when we get to future vertical lift. And the reason that that's so important, as Patrick and Vince showed you, the technology that's going to be brought to bear from an air vehicle perspective is really game-changing, but it's going to be the technology that our forces ultimately fly for the next 50 years. When we look at it from a mission system perspective, those mission systems are going to iterate multiple times during the lifetime of these air vehicles. So what we're really pushing towards is validating the design requirements that will be that digital backbone that's an enduring mission system that in which we can rapidly introduce new capabilities as that pace of change continues to accelerate into the future. In terms of where we're at today, 3 parts of the mission system architecture demonstration, the MSAD. From an industry perspective, we've completed the Joint Common Architecture or JCA demonstration. Got some great lessons learned out of that, validated the ability to procure or develop 2 independent software applications from industry, share those with the government, and integrate those on mission systems we knew little about. Right now, we're just launching into the AIPD phase, the second phase of MSAD. That's an architectural implementation process demonstration. So this is really validating that open system interconnectivity one level up. So working to express an architecture as functionally decomposed by the JCA and apply that to some today real world models of aircraft to again kind of further prove out and provide some risk reduction on that moving forward. The unique piece about this, Rockwell Collins, along with some of our industry partners, are working to exchange models between companies, again, to kind of further prove out the open systems piece and also start to inform what's going to happen as we move into the capstone demonstration, the next phase of MSAD, in terms of what those roles look like between industry partners from an acquisition perspective. So in sharing models with our peer companies in the AIPD effort, it's allowing us to play the role of both the integrator and the software app provider, and we'll be providing a lot of lessons learned coming out of that. And that will all culminate, as I said, in the capstone effort, which will start here in a couple of years. And that's really then bringing that up to implementing a reference architecture and more of a full mission system implementation, and really start to get at some more of that business and acquisition side. So as we move to that, the intention, I think, is for the government to give us in industry a model as a specification from which to go build that mission system, and really inform what the eventual requirements will look like when we do get to a future vertical lift program of record. So the final thing I'll leave you with, in terms of the acquisition model and moving forward and proving out some of the value there, What we've seen a lot of positive in terms of industry and government collaboration through the MSAD process. In our experience at Rockwell Collins, the best results that we've achieved in the systems that we've fielded, we've put together, have always been through a high-level collaboration from the government and our side and industry. And we really have seen that come through strong in the MSAD effort, both in terms of shared investments and a lot of collaboration in the tools and the processes.
Thanks, Ryan. And closing out the opening comments, we have Chris Van Buiten, who's Vice President at Sikorsky Innovations. He runs the Sikorsky Innovations Group, responsible for maturing next-generation technologies, including the X2 technology, rotors, autonomy, and other next-generation products. Chris?
And good morning. I'm filling in for Mr. Nick Lapos, who wanted to be here, but he's in a hospital. So I'm going to give you a vertical lift consortium industry perspective on the power of open systems on future vertical lift. And I'm going to do this using a few examples. Future vertical lift will likely be an optionally piloted aircraft. It'll be able to fly with 2 crew, 1 crew, or no one on board, moving cargo missions with no one on board. An incredible level of operational flexibility for the warfighter. Now let me show you the power of open systems to enabling that. Next slide, please. Industry has worked on the level of computation and computing required to support optionally piloted flight. Just in the year 2000, it would have required 2 complete racks of computers that would fill the Black Hawk cabin, use 1/4 of its payload, and you'd have to fly with the doors open to cool the computers. Just a few years later, it would be a single rack, and now you're down to half a Black Hawk cabin. But recently, in flights demonstrating optionally piloted flight, that computer shrank to the size of a microwave oven and was an easy-to-cool 200 watts. And recently, just 3 years later, it shrunk to half that size while doubling the cores. That change is only possible by adopting open systems and embracing commercial advances in technology and creating architectures that let you fold in the latest hardware, software, and algorithms. That's going to be the power of open architecture systems. We picked this example, that's a 16-year span of time. Think of that for FVL, as Dan mentioned, starting development in 2020. This gets you to 2036. You're in LRIP and delivering airplanes and significantly increasing their capability readily using open systems. Next slide. Let me just share another example. We talk about capability gaps of the current fleet. These are the capability apps page, just like your iPhone, that'll be available on future vertical lift aircraft, that'll let the aircraft adapt to all different kinds of flight regimes and modes. Fly for minimum noise, fly for minimum logistic footprint, minimum signature, do automated terrain following, automated cargo logistics with no one on board. And these kind of applications will be enabled by open systems. The software algorithms, hardware, sensing, computation that supports these apps and constantly grows and infuses new ones into the future vertical lift platform will be enabled by open architecture systems. Okay. But let me give you a cautionary tale, an inside look at some of the issues we're really struggling with open systems. The airworthiness of these future rotorcraft is obviously a significant issue, right? This is a hardware component. As far from open systems as you can imagine, this one happens to hold the main rotor blade onto the helicopter, an important element. And it's sized by the loads it experiences. And traditionally, that is a physical discussion, and testing and measuring of loads. In FVL, that is a cyber-physical discussion, which is an intersection of software, flight control algorithms, and hardware. And let me just give you that example without diving into the physics. Go ahead. Components experience loads, and you have loads over time, and they're all just bends of the coat hanger, and eventually the coat hanger breaks. In traditional sizing tools, you use the red line above. There's the wiggly line. Too hard to understand. We size it conservatively to the red line above. Future vertical lift is going to have more range, more speed, more performance, and it's going to be a lighter weight system sized to the squiggly line, because the computers can actually compute the real loads in real time and calculate the damage that every component on the airplane has experienced, and that lets us cut the size of those components by as much as half. Even more than that, on the next slide, the fly-by-wire flight controls that are both in Defiant and Valor are going to tailor the loads experienced by those components in ways the flight crew doesn't even feel, but that'll further the loads on these components, making them smaller, lighter, less expensive, expanding their lives, reducing the maintenance burden. Can these systems that are so tightly coupled with the physical features of airworthiness be similarly open to kind of the apps we talked about before? That's creating kind of a fundamental challenge in the FAL team of where do we kind of draw the line. Open systems, fundamental to FAL success, but where do you draw the line? Who owns airworthiness? Features like that, okay? Here's one last example. This is an actual airplane out in flight. This is a big data snapshot of a particular maneuver executed by the entire fleet over time. We are going in the FVL world to be using that kind of big data to calculate the lives, expand maintenance intervals, and move beyond an assumed usage to actual usage that lets the warfighter keep fighting with the machine instead of bringing it into the shop, depending on how it is used. Give them a surge capability. And again, that's a cyber-physical interaction of these software systems with physical systems. So the challenge in front of us, huge opportunity with open systems, providing constant capability growth of FAL assets. And the challenge will be balancing that with maintaining the airworthiness of the machine. Thank you.
Well, thank you, Chris. And panelists, I have to commend you for doing a great job of keeping your comments just the right length. So we've got a good amount of time left for questions, which is fantastic. I want to start out, I think as we've gone down the row, we've heard a lot about what's been achieved so far, which is pretty impressive. But I want to ask you a little bit about what's left to do in this, particularly in this technology demonstration effort. So obviously there's an entire acquisition program, we hope, left to do on future vertical lift. But thinking, at least for the moment, a little bit about the demonstration program, I noticed as Dan was going through his slides, the schedule element for both the air vehicle and the mission systems continues out for multiple years. And at the same time, you know, the air vehicles are starting to come together as we saw. So if you could just give us a feel for what's coming up next in this technology demonstration effort, what's left to do. Start.
Sir, I'll throw out a couple of things. So it takes some time to, I think Pat and Vince both said that, you know, the aircraft are coming together nicely, but it'll be late next year before they actually get to flight. And then we've got 150, 200 hours worth of flight time, if you will. And, you know, new aircraft, you don't fly them every day. Generally, you have data reduction timelines. So that's what's really going to take it through 19, I would say. And so what that means to us, I would tell you from a government perspective, what that means to us is, you know, we're sort of past the point. We're at the end stages of understanding that, number one, technology is out there that's available to meet our capability gaps, and that we understand enough about those technologies, about that system, that we could actually move forward in a low-risk perspective to develop a program of record. What's left to do now is to actually put it in flight, which uncovers those engineering issues that'll still have to be dealt with during a program of record development phase, right? So you've got a development phase for the program of record. You'll have to deal with some engineering issues. We always have them, but what we understand today is that the air vehicle's probable, it's affordable. On the architecture side, so I talked about 3 increasingly complex demonstrations. Ryan sort of hit on that. We finished the JCA demo, by the way. We only had 2 of industry on contract for that, but the industry at large learned from that. That's the collaboration that's going on in this process. Now we have 6 partners in AIPD hope to continue that growth, if you will. But this demonstration is about that implementation, sort of the business case piece. The next one, the capstone, if you will be a couple of years long, and that really is the culmination part of bringing together a plan for implementation of open architecture.
So if I could add, certainly, as Dan said, the focus is not only on flying a vehicle and expanding its envelope, but we continue to collaborate with our customer. They are trying to develop the requirements for future vertical lift. We need to make sure that they understand the technical capabilities across the board, not only for their vehicle, but for the mission systems. And so it's just from the next several years just to continue tech maturation of a whole scheme of technologies that'll be blended together into future vertical lift.
And if I can add real quickly, well, our vision is once we've done the basic flying and prove out that the air vehicle does what it needs to do, it becomes a potential tech demonstrator. We've built the aircraft to fly, for 200 hours, but it is Bell engineered, so I think we're going to fly for much further than that, given the conservatism that we're known for. So we'll have lots of opportunity to fly. I see it analogous to a tech demonstrator that we had with our Boeing partners on the V-22 program. We actually leased back an aircraft, and we've done lots of demonstrations on that have turned into capability development. Looking to keep sand and dirt out of the engine was one of those demonstrations that has led to a program, and there are others. So our vision is, once we do the key things we want to do up front, which is prove out, how the vehicle flies. There's myriad tasks that we can do after that, from electronic capability, sensors, those kinds of things, to new and better ways of for mechanical systems.
Thoughts on what's left to do on the mission system side of the demonstration?
Yeah, so I think as Dan alluded to, moving forward on the mission system side, the focus in the next year is on the AIPD side, building towards that capstone. So a lot of work in expressing the system within the functionally decomposed.
Could you just, AIPE is?
Oh, sorry,
English.
the architecture implementation process demonstration. So again, that second step of the increasingly complex demos, as Dan mentioned, 6 companies working on that. And so I think a lot of the work left to do there is in validating the interoperability between the pieces. And I would say some of the lessons learned early on, even just from the JCA demo and some of the efforts that the team's undertaken so far is as we express the system in models and expect models to talk between 2 different entities, 2 different companies, we found that there are instances where good, smart engineers can meet the letter of the law in how those things talk together, but maybe we miss the intent of what the open system architecture was supposed to be. So I think there's a lot of learning to continue to go on there in terms of capturing in those data models the real meaning between those, and then really looking forward to validating that when we get to the demonstration part of AIPD at the end of this 12 months, moving that into capstone, like Dan said, where we'll take that to a higher system level and really start to hit on some of the tough questions that I think will come up as we start to look at how do you marry the mission system back with the air vehicle, where are those boundaries, and how does that work from an acquisition perspective? I think those are all still tasks ahead of us from an industry perspective.
I'm excited that while we build these 2 fabulous demonstrators, industry and the government will collaborate to find the cost capability sweet spot, right? What is that best value warfighter capability, affordable for the nation? And closing on that is going to be a very important job in parallel with the technical demonstrations.
Great. I'm going to throw one more question at the panel, and then we'll turn to the audience. One of our previous events, we focused on the issue of commonality, which may be a little bigger than the tech demonstration as an issue. We've talked a lot this morning about open systems architecture, which is related, but not quite the same thing, right? You could have very different subsystems that meet the open system standard, but wouldn't necessarily be, significantly common with one another. So I'd just be interested in folks talking about, is one more important than the other? Are these complementary but very different priorities? And how does it fit together?
I'll start as well, again. So commonality, like open system architecture, has a different definition for different people, number one. So you have to define what it is you're after first. So from a commonality perspective, there's two focuses, I would think, from an FVL community point of view. One is, parts identicality or, interchangeability, and then you've got the interoperability piece. And certainly interoperability piece from a warfighter perspective is very, very important, and there's opportunity for that. But if you will, the commonality for us is not about driving the air vehicle parts count to zero, right? That they all share the parts. It's about providing that interoperability in a larger sense. So can we build efficiencies into the life cycle management of our aircraft and have our services interchange in various ways? So I would say that it's complementary, your question, but the architecture is fundamental in that process. So an architecture that would allow you to buy commodity-based subsystems and efficiently integrate them provides the opportunity for commonality and interoperability between the services, right? So I almost say that the architecture is, if I trace it back, we have common pieces today. We have a common component of a radio today, but the efficiencies of having that common radio are not really realized, because when you integrate them on the various service platforms today, it's very inefficient, because there's not an architecture that's built on the same standard, the same tools, and the same processes that allows you to integrate it efficiently. There's always some level of integration, so it's probably good that we continue the process of common subsystem components. It's more important that we build a backbone on the aircraft so that it can efficiently integrate, and you can use it as a commodity-based approach.
So certainly, I think as I see it, commonality drives down cost, it simplifies training, and it's a challenge for industry. Certainly the start is, as Dan and his team are working, they're introducing standards like the FACE standard and the host standard as applies to avionics and mission systems that we all can rally around and work towards. But beyond that, it is a challenge on, as I develop and as we field our vehicle, what's Vince going to do? What parts does he implement back into legacy aircraft, common aircraft, to continue to make this aviation element efficient? And so that is our challenge.
Yeah, so they are different, but I'll talk the commonality piece. We believe strongly in commonality, and we've seen it in action. On the H-1 program for our Marine Corps customer, the fact that the attack version and the utility version of the H-1 are 85% common pays huge dividends, and we've learned a lot from that. It definitely drives down the inventory that you have to stock. It makes things cheaper, more efficient. Less logistics tail to move, and so we intend to continue that going forward, because it truly is beneficial to have commonality. It's just math. If you've got more aircraft using the same parts, the math says it's going to cost less and you need fewer parts out there. So it is important, and we see that as different from open system architecture, because the open system architecture, the whole point of that is to drive down the number of boxes that you need to start with, and to focus on the key pieces like the sensors and those kinds of things, and do the processing in some kind of common location. So they are different, but obviously both important.
Yeah, and I would just add, I think both commonality and interoperability are core tenets of open systems, or where we're going with open systems today. The interoperability piece is provided by those standards, so as you look at the digital backbone that might support a family of systems, if it's done correctly, and it provides that interoperable piece, so you can move components between aircraft as needed. But really from a commonality perspective, as you look at costs across acquisition programs today, you know, the ever-increasing cost of software or the ever-increasing portion of software cost relative to the overall cost of the platform, it'll become more and more critical to be able to port those capabilities or only invest in that software capability one time on one platform and then be able to make it common and interoperable through having the right backbone in place to move it in between platforms.
I just add, kind of building on Vince's point, the Black Hawk and Apache are fantastic aircraft that serve the Army in spectacular fashion. The opportunity to drive their replacement to be much more common is potentially game-changing for the warfighter, both to match operational capability, but also logistics and life cycle cost. And the additional opportunity is to leverage the FVL-developed technology. Maybe it's on the mission system side, and push it back into the legacy fleet. Some of the legacy aircraft will be operating past 2050, and for them to be able to leverage this technology through commonality is a very exciting proposition.
I want to open up the questioning to the audience here, so if you have a question, raise your hand. We've got folks who will bring a mic. Just briefly introduce yourself, ask one question that is a question, and we'll get in as many as we can. So, Laura, we'll start up here.
Thank you. Hi, Lara Seligman with Aviation Week. You talked a little bit about commonality. Can you talk about commonality across the services as well? So Marine Corps, Army, Navy are all potentially getting something like this platform. So how common is this going to be across the services? What have we learned from the Joint Strike Fighter program? What lessons have we learned that we can maybe apply to FAL?
So our discussion in general was multi-service. So we weren't talking from an Army perspective. I think all the comments you heard were multi-service. So the requirements, IPT, no different than the acquisition or S&T IPT under our construct for FEL, are joint from the beginning. So when we talk commonality, we are talking joint. Jointness can come via both services using a common platform, i.e. the H-60. The H-60 is a common platform. There's a lot of commonality in that aircraft across all the services and agencies today. So that's an opportunity. So the requirements community is actively working on where can we draw that common space, okay, for a platform. But then I want to branch it further and say that just because they're not a common platform does not mean we can't have joint or multi-service commonality. So we go back to that architecture. If we have two different air vehicles at two different size points in different services, we can have an architecture predicated on the same standards and the same processing and the same tools that allow for all the subsystem commonality to go across multi-services. And I think that's where we're focused.
And this is a fun one. As a Sikorsky employee who's now a proud Lockheed Martin employee, I've had a chance, to your Joint Strike Fighter question, to walk the Joint Strike Fighter line in detail, and it's miraculous how on one line the Air Force, Navy, and Marine variants, some hover, some don't, some are carrier, some are fixed wing, they are built on a single line. And there's tremendous commonality that at times can go all the way down to the machine code that's making a particular frame, and that particular frame drops into the line. But one common line that makes those three variants with three very different capabilities, but a high degree of commonality, and kind of redefining what commonality is, but generating significant logistics opportunities and cost savings to get those three variants. It'll be exciting for the rotorcraft industry to learn some of those, drag some of those techniques into the rotorcraft build for FEL.
Arguably, it took a really long time to get to the point where there's commonality that actually directing cost savings.
Sure.
JSF. So what are some of the lessons learned that you can take away from this program?
Well, that gets to the government, how the services unify in requirements. And those will get to those trade studies of capability versus cost for FEL. You can imagine a tiling of requirements that could make FEL enormous and very expensive, right? So we've got to avoid that. But some of these techniques, like they use on JSF, can mitigate those costs while providing joint capability.
I was thinking about that on my joyous commute in this morning. And it occurred to me that at least on the transport side, all of the helicopters are multi-service. I think they've all been used by multiple services. So as opposed to the history with fighters where the multi-service history was a checkered one, with helicopters, it's been almost the norm.
It is the norm, although it's somewhat forced norm, right? So if you think about the H-60 as a platform, I'll use that as another example. The Army went forward with a program, it developed that program, and then other services said, hey, that's a good platform, let me modify it to my needs, right? And so that's not the most efficient way to do it. So the most efficient way to do it is to get together beforehand and put the hooks into the design. And what's different from the argument in the past, I believe, of putting too many requirements, if you will, onto one platform. What's different is what Vince talked about. The modeling tools, the engineering assessments, the competencies that we use today to design an aircraft are much higher fidelity. So you can put hooks in, say, for marinization on a design that will not cost you very much. It will not hinder the design for an aircraft that's not going to be marinized, as an example, because your design capability is such a high fidelity today as compared to what it was in the 60s and 70s. So we want to go in with that up front.
Question here?
Yeah, hi, Mike Hirschberg, the director of AHS, American Helicopter Society International. There's a question for Dan. So Dan, I really appreciated you opening, your first statement was, JMR is not FEL, and that's, I think, commonly confused in the media and maybe even people who should know better. But so there's a fantastic demonstration that the industry is doing with JMR, with the mission systems. And I do believe that the industry can do things faster and can accelerate that. But one thing we've talked a lot about commonality, the word engine has not come up, at least I don't think it did. So there's been some discussion in the press about, is it FVL or is it ITEP, whereas I think both of them have a compelling and separate need. But so Dan, I guess if you could comment on engine and specifically FVL, ITEP, and other engine programs. Thanks.
So I'll touch as far as I can go. Obviously, I'm not the program manager for that, but I will tell you from an S&T involvement perspective. So as the S&T sort of lead for FVL, we're heavily involved, and there's been a portfolio approach to engines, and it continues today, right? So ITEP is the program that came after the S&T program, AATE, right? The Advanced Affordable Turbine Engine, I believe it was. So that S&T engine led into ITEP. ITEP is fundamentally to keep our legacy aircraft, Black Hawk and Apaches, relevant. As someone said, I'm not sure who it was, those aircraft are going to be out there for decades to come. It will take years to replace all of the Black Hawks and Apaches. We have to keep them relevant. So ITEP is needed. Matter of fact, it's listed as the Army's #1 aviation priority. And that's important because it will come before an FVL solution comes. So what's the engine for FVL? We don't know. At this stage of the game, what we can project is what the designs might need from an installed horsepower perspective, from a form fit perspective, from a type of engine perspective, meaning variable NP rotor capability, not. So we have essentially established an S&T portfolio that provides the technologies for that various capable engine, if you will, the various capabilities of an engine. So we've laid the groundwork, we believe, in the S&T program. What we've done in the S&T environment for JMR is allowed the companies to provide a system-level approach to the aircraft. So the companies chose engines that were readily available based on the time and the limited resources we had to conduct JMR-TD to provide a system to us, the government. Right now, the acquisition strategy for FVL is to take the same approach, to let the platform provider provide a system, if you will, including an engine, for the performance that we're looking for. And at that point in time, whether it's an ITEP or an ITEP variant, or whether it's a new centerline engine, or whether it's a modified engine with what we call FATE, Future Airborne Technology, what is it? Engines. There you go. I should have known it was engines, right? E. But so those technologies that are out there, we can modify existing engines for that solution. So the approach right now is that ITEP's required, legacy focused, provides a basis for potentially FEL solutions across the family. Fate out there from an S&T point of view is providing the backbone for other engine capabilities, and the system that comes to an FEL program of record will come with an engine to provide the capabilities and performance that we're looking for. That answer?
Dan, I would just add the Marines used that approach to great effect on the 53K. They gave Sikorsky the authority to run the engine competition and develop the engine with the manufacturer and integrate it in the system and deliver a complete system. And that's worked quite well.
Yeah, I just want to be clear that, I'll speak for Bell, we would not have invested what we have invested in the tech demonstrator, to lead to FEL without making sure that we are talking extensively with our engine manufacturing partners to make sure that there will be an engine, whether or not there's a formal program or not. We will ensure that there's an engine that will be available to power the V280 should that go into a program of record and go into production.
Just in terms of the two demonstrators, what engines are they using?
The Bell's using the GET 64.
We're using the Honeywell T55.
Otto Kreischer with Sea Power Magazine. Maybe going contrary to the cross-service commonality piece, Mr. Donnelly, for your tilt rotor, the Marine Corps, if they would buy it, or the Navy too, they'll want something that they can stow aboard ships. And the V-22 obviously has the rotor wings that rotate around for storage capability. Obviously, you're not going to do that in your initial demonstration model, but is that something you're thinking about if the tilt rotor becomes system of record, to rotate those the wings and for shipboard storage?
Go ahead.
Do you want the tilt rotor guide, or you want Mr. Donnelly? You got to pick one. I'm going to assume you're talking about the tilt rotor. Our view is that as for V-22, there'll be some customers who want to potentially fold the aircraft, and some that maybe will not want to, because there is obviously a weight penalty. Our view is to make everything from the wing joint up, where the wing joints to the fuselage, the same, and then allow that same wing and drive system to be attached to a fuselage that either allows it to rotate or doesn't. So again, trying to stay as common as possible. From our view, tilt rotor magic happens from the wing joint up. We want to keep that as much as we can the same, and we'll vary fuselages to accommodate particular customer requirements.
And if I could add, in our configuration, we are certainly also very conscientious about supporting all the services. So we're aware of the box size and the weight capability of the littoral combat ships on up. And as such, we will demonstrate blade fold in our tech demonstrator. But as Vin said, we'll accommodate as we go forward.
Yeah. So when the government asked industry to design these aircraft, we did not force the aircraft to be completely capable, meaning it has to fold to go onto the ship, or a certain size, or any other thing, whether strategic deployment. What we did was made sure that they designed it so that it did not prevent such a design, if you will, right? So just because we won't demonstrate it, we ensured that the aircraft design, the basic fundamentals of design, wouldn't be hindered by that. Okay.
We have time for one more question. We have two questions, hands raised. So what I'm going to ask is if we'll bring two mics around. Sam, if you'll come down here to the front. And Sydney, and if you could each just ask your question at one after the other, and then we'll have the panel answer them all together.
Good morning, gentlemen. Thanks for your presentation. My name is Air Commodore Tenaf. I'm the Dutch Defense Attaché. The question I have is, what are the thoughts in the panel about internationalization of the program, like we did with F-35?
And Sydney, we'll ask your question, then we'll.
Sure. Sidney Friedberg, Breaking Defense. On the subject of making it optionally unmanned, I mean, obviously there are not requirements set for FVL yet. That would be sort of jumping the gun. But how big a part of the thinking is that currently, and is optional manning something that's being explored at all in the current stage with JMR, which is obviously, as people keep saying, a different thing?
All right, so we'll go down and answer these. I will tell you that we have upcoming events in this series on both of those questions, so stay tuned.
Yes, right. So, Sydney, as I just said, it's no different than shipboard compatibility. The optionally piloted piece was put in there as it will need the hooks, right? It will be possible to make it optionally piloted. And we are doing active work in terms of the study of what that means. Do you design a cockpit with 0 pilots to 2, or do you design a cockpit from 2 to 0? It's different, right? The outcome's different. So we're doing that kind of work. We're starting down that process. I would tell you, these aircraft are so highly advanced, right? The fly-by-wire flight control system, it's ones and zeros going to the servos. Doesn't know any difference, whether it's coming from your meat servo or from a computer that says this is where you're flying, right? So ultimately, these aircraft are going to be highly integrated. They're going to fly where you tell them to go, and you're going to do most of that pre-mission planning. The pilots are there for other reasons, whether it's mission command, whether it's adjustments on the mission on the fly. So doing that work, we've already started down that path. Internationally, so we had one issue or one opportunity, if you will, to bring international requirements discussion together. I think that's going to continue. We'd have to, right now we're focused on that requirements generation piece, starting the program of record, if you will. So the acquisition and the requirements community would really be the place to focus. From an S&T point of view, I would say we're already international. So the S&T community has tons of partnership agreements out there working on technology. As a matter of fact, going over to NATO myself first week in October to Italy for that very purpose. My boss, Dr. Lewis, is right now in Australia, right? So that kind of partnership across the S&T community exists today. I think it's pretty robust.
So, Chris showed a picture of a little dial that goes from 2, 1, and 0. Certainly, as he emphasized, it's the flexibility that is brought forward if we go optionally manned. And as Dan said, as we are developing our technology, Sikorsky is flying a couple of aircraft unmanned as we speak. Boeing and Lockheed have a depth of technology that we can draw on, but certainly as we look at our particular configuration, we're actually looking at what else we can do to enhance its capability if we went optionally manned, including taking out the cockpit.
As far as the international question, obviously we would be subject to what our DoD customer wanted, but I will say that it would not hurt Bell's feelings at all if there were international partners involved. So, but on the record, deferring to Dan to determine that. As Dan did say on the optionally piloted piece, it is about ones and zeros. We are a fly-by-wire system. I'll say again, just yesterday we announced, our development efforts on the V247, which is a UAV. Some people want to say 24/7. That works too. But the fact of the matter is, we're leveraging the same technology for flight controls that come out of V280, and we're going to do that unmanned. So going back and making the V280 unmanned as well, nothing's trivial, but it's something that we have in mind and are planning to do.
I think that model on the international collaboration on JSF has added a lot of value to the program. It's added stability to the program. It did add complexity, but I think that's been managed quite well. And I think that is a real option, and now we've got real data and experience to use that option here.
And one of the reasons I mentioned I think we will have a future event on this topic is because we'll get the right government folks who can speak to it. Dan, I think, is not the right person to commit the government in any direction on that international question, so I'll try and rescue him. But this has been an excellent discussion. Thanks to everyone for coming, and I want to thank the panel for doing a great job. So.